Hello class, so this is the second video in section 4.6. So in the previous video, we talked about Rogers theorem, right? And we did an example of how it works. There were three conditions we had to verify, and then if Rogers theorem applied, it guaranteed us the existence of a critical point. So that was the last video. Now we're going to talk about, I guess, the next step in Rogers theorem. So it's called the mean value theorem, and it is basically a stronger version of Rogers theorem. So it is more general. It applies to more things. So you're going to see that that's the case because the difference between the mean value theorem and Rogers theorem is that here we're not going to require the endpoints to be, the function evaluated at the endpoints to be equal. So remember in Rogers theorem, we had an assumption that f of a was equal to f of b. Here we're going to have the same first two assumptions, right? I mentioned those are going to show up in every theorem we see. Right, so f is going to be continuous on the closed interval AB and differentiable on the open interval AB. Those are the only two conditions we need. So we drop the condition that f of a equals f of b. As long as those two conditions are satisfied, then what do we get? There is at least one input, c, in the interval AB, such that what? F of b minus f of a over b minus a equals f prime of c. Okay? So that's what the theorem says. Now let's go ahead and unpack it a little bit. Specifically, I want to see what is this actually telling us, that f of b minus f of a over b minus a is equal to f prime of c. What is this saying? Okay. So recall that this expression f of b minus f of a divided by b minus a, that is the slope of the secant line through those 2 points. The slope of the secant line through where? So through the points. And so remember, secant line, you need 2 points to find the slope. All right, so what are the points? So through the points a, f of a, and b, f of b. And I'll draw a picture of this in a moment. So after I write this out. So this is saying, okay, the first part of the equality, or the left-hand side, is saying, okay, that's the slope of the secant line through these 2 points. What's the right-hand side of the equality? Well, this is the slope of the tangent line to the graph somewhere inside the interval AB. This is the slope of the tangent line to f, remember, because we have a function f, somewhere inside the interval AB. So what is this saying? Well, we can always find an input inside the interval AB such that the slope of the tangent line to the graph equals the slope of the secant line going through the endpoints. Okay? So word-wise, that's what it means. Let's go ahead and draw a quick picture. Okay. So let's see. I'm going to draw. Let me plug in, put in my A and B. Say A is here somewhere, B is here somewhere. And we have that f is continuous and differentiable. Right? So I'm going to write f here for one endpoint. Now remember, the endpoints don't have to be equal. So I'm going to write f of b here. So this is f of a. This one here is f of b. So again, we drop the condition that f of a equals f of b. I'm just going to draw my function. Now, of course, it has to be continuous. So when I draw it, I can't lift my pencil up. And it also has to be differentiable, meaning it's smooth, right? So no sharp edges and no places where the slope of the tangent line would be vertical. Okay, so how can I draw it? Let's just do something that looks pretty smooth. Something like this. Something like that. That's pretty smooth. Okay. Now, what is the mean value theorem saying? And this is f. Whenever you have a situation like this, when your function is continuous on the closed interval AB and differentiable, there must be a place in an input where the slope of the tangent line equals the slope of the secant line between the endpoints. So let's first draw the secant line. Okay, I'm going to draw it as an orange dotted line. Okay, that wasn't too bad. So that's the secant line. And if you see here, let me draw it in another color, let's use blue. It seems to me that right about here, the slope of the tangent line seems to be equal to the slope of the secant line. So maybe right about here. Actually, that seems a little bit too vertical, so maybe around. So I want to get it right in the picture. So there's this. Okay, let me trouble just erasing the. Okay, there. So one last try. There's third time's the charm. Yeah. So it seems like right about there. So that should be touching the function. That's okay. It seems like right about there, the slope of the tangent line is equal to the slope of the secant line. And you can see it, right? The lines, the blue line and the orange line seems to be parallel. And that's what this theorem is saying. That's what the mean value theorem says. Right? As long as your function is continuous on the closed interval AB and differentiable on the open interval AB, you're guaranteed at least one place. And again, this is not saying that there is only one C. There is at least one input. So at least one C. There could be more. But there is at least one C where, what is this saying in mathematically wise, so that f prime of C equals the slope of the secant line between the endpoints. Right? And again, you can see it graphically that it seems like this line C, which is the tangent line, is parallel to the secant line. Remember, parallel lines have the same slope. So that's what this theorem is saying. We can always find such a C, such that you can draw a picture like this, where the tangent line is parallel to the secant line. So that's what the theorem is saying. Now let's again do an example, just like we did in the previous video. Okay, so does the mean value theorem apply to f of x equal to ln of 2x on the interval 1, e? If so, for what values x is that satisfied? So what are the x values such that the slope of the secant line, of the tangent line equals the slope of the secant line between f of 1 and f of e, right? Those two values, okay? And there's another function we test. Okay, what about for g of x equals 1 minus absolute value of x on the interval negative 1, 1? Okay. So we have to be careful here. We're going to do one at a time. So let's start with the function f on the interval 1 to e. Okay. So starting with f of x equal to ln of 2x on the interval 1 to e. So first of all, the two conditions we have to check is that our function has to be continuous on this interval and differentiable on the open interval. Okay, so 1, is f of x continuous on the interval 1 to e? Well, it is. Why? Because we know the natural log function is continuous, so let me just do a sort of graph argument. So what does ln of x look like? Ln of x looks something like that. It's continuous everywhere in its domain. What's the domain? Well, the domain is 0 to infinity. And this is just ln of x. So it's continuous definitely on the interval 1e. What is the 2 doing? Well, all the 2 is doing is either shrinking or stretching our graph horizontally. That's all it's doing. It's either stretching or compressing horizontally. So what does that do? Well, that's not doing much. That's not changing really what the graph is. Maybe it looks now something like this. So it's a little bit stretched or compressed horizontally. But the property of it being continuous and being differentiable, in fact, is still it's still maintained. So the fact that we're stretching or compressing a function doesn't change whether it's continuous or differentiable. So this is a graphical argument for the reason why this is continuous. If you wanted more of just an algebraic argument, you can just say it is continuous because multiplying the x by 2, you can treat it as a composition. Right? So graphically, we can see that it is the case. So graphically, we can see that it is continuous. How would you do it algebraically? What you would do is, like I said, use the fact that this is a composition. So algebraically, ln of 2x equals f composed of g. You can write it as a composition where what's the outside function? The outside function is the natural log, and the inside function is just 2x. Kind of like in in the previous example with sine of 2x. What theorem do we have for continuity of compositions? Well, if they're both continuous, then the composition is. Okay. So that's how you would do it graphically. Because both functions are continuous on the interval 1e, so is the composition. So that's how you do it algebraically, using things we've learned in this class. So either way works, whether you want to do it algebraically or graphically. I'm fine with either as long as you show your work. Okay? So the first part works. It is continuous. Now for differentiability, it's the same thing. I already gave you a graphical argument, and you can also do a composition, because what does it mean to be differentiable? That the derivative exists. Right? So you can find the derivative of this using the chain rule. Right? So as long as you can find the derivative and it exists on that interval, then it's differentiable. So what's the derivative? We need to use the chain rule. Oh, and let me not call this f, because f is the original function. So instead, let me call this h. So h of x and g of x, call h and g. Yeah, because f is the original function, so I don't want to use that letter name twice. Okay, so to find differentiability, just find the derivative. It's the derivative of h composed of g. By the chain rule, this is h prime, leave the inside the same, multiply by the derivative of the inside, which is equal to what? Okay. So it's the derivative of h. H is ln of x. So that's 1 over x, right? Then you leave the x as 2x, because you leave the inside the same. It's 1 over 2x times the derivative of g. G is 2x, the derivative of is 2. This is just 1 over x. And of course, we look at this function. It exists on the interval 1 to e. Right, so it is differentiable. Since it exists on the interval 1 to e, it's differentiable. Because remember, that's what differentiable means, that the derivative exists. Differentiable on interval 1e. And again, for differentiability, we use open interval. Right? So it does apply. So let me go to another page. The mean value theorem applies to f of x equal to ln of 2x on the interval. So let's use again the whole interval because it works everywhere, 1e. Now, the next part of the question is, now that we know that the mean value theorem exists, we want to know, okay, for what values of x is it satisfied? So for which inputs in the interval 1 to e does the slope of the tangent line equal the slope of the secant line between the endpoints? Okay? And again, we're guaranteed to have x values where this is true. That's what the mean value theorem says. Okay. So let me just write that. Let me write mean value theorem. So MVT for this mean value theorem. So I'm just going to write it once. So from now on, if I write MVT, that means mean value theorem. So by the mean value theorem, there exists at least one, not once, at least one x in the interval, open interval 1e, such that what? Well, f prime of x equals what? Well, the slope of the secant line, which is, we actually calculated, it's f of e minus f of 1 over e minus 1. Okay. We want to find what x values satisfy that. So let's go ahead and simplify this expression here. Okay. So what's f prime of x? So we found that, right? So we found that f prime of x was just 1 over x. Okay. What's f of e minus f of 1 over e minus 1? Okay. So f of e, remember f is, I'm going to write it here, f of x was ln of 2x. So f of e is ln of 2 times e. So we have, so the other thing we have is f of e minus f of 1 over e minus 1 equals ln of 2e minus, so ln of 2, just plug in 1 for x, minus divided by e minus 1. Okay. Now this we can actually simplify algebraically. You could use a calculator to approximate this, but here what can we do? We can use some properties. If you remember, subtracting logarithms is the same as dividing inside the logarithm. So it's actually just ln of 2e divided by 2 over e minus 1, which is ln of e on the top, right? Because the 2's cancel. What's ln of e? Remember, those are inverse functions, so they cancel out. So cancel out, it becomes 1 on the top over e minus 1. Okay. So what are we trying to find then? Then we're trying to solve f prime of x equals 1 over e minus 1, or 1 over x equals 1 over e minus 1. Right? And again, that comes from f prime of x equals 1 over x, and we're setting it equal to the slope of the tangent line, of the secant line, sorry, between the endpoints, which you found to be 1 over e minus 1. So that's it. This is f prime of x equals 1 over e minus 1. Now we just solve for x. So multiply both sides by x. I'm going to do it step by step. So I have 1 equals 1 over e minus 1 times x, and divide both sides by that. Right, so divide both sides by e minus 1 over 1. So we get e minus 1 over 1 equals x. And that's the answer. So again, what is this saying? If you plug in, if you evaluate f prime at x, which was e minus 1 over 1, and this should be equal to the slope of the secant line, or f of e minus 1, f of e minus f of 1 over e minus 1. Okay. And that's basically all the problems that you're going to see like this. If the mean value theorem actually applies, you'll be able to do something like this. You verify first that it applies, right? So you check both conditions. Your function is continuous and differentiable. Then you simplify everything, right? Simplify f prime, simplify, find the slope of the secant line. From that, you get this equation here. The left side is f prime. The right side is the slope of the secant line, and you solve for x. Now, there was another part where we needed to work with the function g of x equals 1 minus absolute value of x on the interval negative 1, 1. Okay. So now let's work with g of x equals 1 minus absolute value of x on negative 1, 1. Does the mean value theorem apply on this interval? Now, for this, the easiest thing to do is just see how it looks like graphically. So how does this function look like graphically? Well, it's the absolute value function flipped about the x-axis and moved and shifted up 1 unit. So what would it look like? It would look something like this. And it's 0 at 1 and 0 at negative 1. So looking at that function on the interval negative 1, 1, does it satisfy the mean value theorem assumptions? Well, certainly the function is continuous. We can draw it without lifting our pencil. But if you see it's a differentiable, it's not, right? Because we have that sharp edge at x equals 0. So it's not differentiable at x equals 0 because we have a sharp edge. So the mean value theorem does not apply on this interval. Oh, yeah, I said I was going to write MVT, right? So the MVT doesn't apply on this interval. So this is a case like something we saw before, where whether this applies depends both on the function and on the interval. Because if you just switch the interval here, let's say, what if we switched -1, 1, or something like 1/2, 1, and leave g of x the same, you would see that now the mean value theorem does apply on this interval, right? Because on that interval, 1/2 to 1, the function is differentiable and continuous. Okay, so what's the thing to note here is that whether the mean value theorem applies depends on both the function and the interval. Sometimes if you change the interval, the mean value theorem now applies. Or if you leave the interval the same but change the function, then the mean value theorem applies. So it really depends on both the function and the interval. Okay. And that's how you work with the mean value theorem.